Hello everyone. I'm Dongze from the National X-ray CT facilities of the University of Manchester, and now I'm the start of the second year PhD student. And I'm mainly working on the multi-scale characterization of the composite tubes. So today I will report some progress on the image-based modeling of the 2D braiding tube under the torsion load based on the synchrotron X-ray CT data. And before I introduce my work, I will answer three questions. The first one is about what is the fiber reinforced composite and why I choose this kind of material. So fiber reinforced composites are kind of material was reinforced by the fibers, including the short fibers or long fibers. Compared with the normal alloy, this kind of material has a lot of advantages, such as high strain to weight ratio. You can see the composite bicycle lifting angle, and this also provides good flexibility of the design. It can be tailored to different shape, different size, and also it shows good fatigue and corrosion resistance. But because of there are a lot of different manufacturing methods, so the fabric, the structures of fabric are kind of complex. So actually, for the damage behavior or damage characterization of the composites are not so clear. So that's also why I focus on this topic. And another one is I will introduce what is braiding and why I choose braiding. Braiding is a kind of manufacturing method to form the fabric or the rope-like structures by interlacing the strands. And shown by the video is braid the fabric on the mandrel to form the braiding tube. This is for the 2D braiding. And the braiding process is automated process with a lower cost compared with the woven or welding manufacturing method. There are a lot of the braiding products, especially for the composite products. Shows at the right part of the PowerPoint. You can see the difference for the golf shaft or the transmission system of the bicycle or the drawing. So third one is about the aim and objectives of the presentation. In this project, I want to combine the two different models. One is about the idealist model of the tube, and another one is the image-based model. Because from the experiment, especially for the in situ, the CT scanning experiment, we can find how damage occurs and how damage propagates. But some kind of elements, experiments are kind of money costing or time costing, so we cannot cover all the process of the material design and optimization by the experiments. So I want to do part of the simulation and part of the experiment and combine this to different aspects and to find a proper or efficient pipeline of the material design and optimization. So based on the CT scanning data, I want to do the image-based modeling to figure out the damage area, and from the braiding function, I will do the idealist modeling to finally to compare this to different model. So this final objectives of this project want to figure out one is about the defects caused in the manufacturing process, whether this kind of defects has an influence on the mechanical performance. And the second, want to find the deformation, especially for the bundles during the braiding process, whether it has the influence on the mechanical performance. And third, want to compare whether these two different models has more accurate expectation of the mechanical responses. So this is about my material and the geometry. The material is a carbon fiber braiding tube. It's a 2D braiding with one single layer. It's a 1x1 diamond braiding method and with a 45 braiding degree. And the material system is a T700 carbon fiber with epoxy. We're using the vacuum infusion method to do the consolidation. And Then I will introduce my main characterization technology using the time-lapse X-ray CT. And compared with other non-destructive test methods, CT technology is advanced non-destructive method because it can provide 3D information of the samples, and at the same time, it also can provide the abilities of the scanning the sample during before or after the loading and before or after the sample degradation. So yeah, this is a setup of the experiment. The experiment was finished by my former colleague named Yuan Chai, has graduated from the PhD at 2020. And I'm following his work to do the simulation and to do other experiment. So this experiment was finished at the diamond light source S13, that's using the open frame rig in the middle part. And after scanning all the sample at different load conditions, we can get a slice like the shoes. Yes, this bundle inside and this epoxy bundle and epoxy. Yes. I think for the data processing, the most challenging part is about to segment the different orientation bundles, because for the carbon fiber bundle, to be honest, they are the same material. That means they have the same densities. They have same the atom number. So actually, this is the two bundles at the slice. This is two bundles. So no boundaries between these two bundles. So for this, I developed the fiber tracing result to solve this, fiber tracing method to solve this problem. Based on the CT data, using the threshold method can divide the bundles into two orientations, epoxy and the pulse. And based on the bundles in the two orientation, can use the fiber tracing method. Fiber tracing method first to trace all the to find all the cylinder informations of the image, and then based on the cylinder information to trace all the fiber lines, to trace all the cylinder as a continuous fiber lines, then can select the fibers in different orientations and transform the lines to the label file and transform the file to the FEM model, and transform the model to Abacus to do the following image-based simulation. So there's some results of the fiber tracing result. The yellow part, the yellow and the green part is the fiber bundles in the two different orientations, and this is a combination of these two different orientations bundle. And after this, can transform the geometry of the fibers to the label, like shows in the video. There are some pores at the inner surface of the tube, and this is a positive 45-degree bundle, and this is a negative 45-degree bundles, like shoes. And then can transform the labeled file to a FEM model, and the model size is the same with the scanning area. So this part of the samples, and the boundary conditions and the loading is also same with the experiment. It's fixed at the bottom and at the torque at the top of the surface. For the FEM model, it also contains 3 parts. This is okay, I don't know why. This is the bundles. This is the pores at the inner surface, and this is epoxy, and all the materials parameters came from the literature, and yes, this is FEM model because the element size is too small, so cannot see the single element from this picture. Yeah, and this is the simulation result under the torsion load. There are 2 different models. The first line is the tube with the pores, and the second line is the tube without the pores. And this is the whole model, the bundles with epoxy. I select the bundles for show the damage area, and I enlarge the damage, the dangerous area of the bundle. So compared with the experiment result, this is the experiment result from the institute experiment. So we can see that the damage area from the located at the bundles are similar with the experiment, especially for the initial area of this part and this part. Yes. And besides, we can see the damage area of these two different models are also similar. So we can conclude, oh, this is a 2D damage showing of the damage. Yes, it's a compression of these two bundles. You can see the debonding, inter-2 debonding, and inter-2 cracking. So we can conclude that the pores in the epoxy do not have so many influence on the mechanical performance of the tube, and at the same time, the dangerous area of these two different models are similar. So I also conclude the strain stress curve of the experiment and simulation. There are 6 lines in the picture. The marked blue line and the marked red line are the volume fraction and the area fraction of the cracking and the debonding, and the green line and the black line are the experiment result, especially for the institute. The black line is the institute test result, and the pink line, the red line over there is the result of the simulation result. So from the elastic area, we can see the accuracy of simulation is in line with expectation. So yeah, that's a good news for me. And besides, we can see from the two different lines are also the same one, especially for the image-based model with pores or without pores. They are almost similar. We can also conclude the same conclusion that the pores in the epoxy do not have so many influence on the mechanical performance. And the more interesting things, combined with the simulation lines and the experiment lines, the experiment strain stress curve and start to bend at the 1% strain loading point. But from the experiment, we can only capture the damage from the 1.5% strain loading point. So I think there may happen something before the 1% strain level. But from the experiment, because we also scanned the sample at the 1 point strain level, so didn't find any cracks or any damage. So yeah, may happen something, but for now I'm not so clear what actually happened or something, or have make some mistake during the simulation. But yeah, I'm not sure really, and I'm happy to discuss. So conclude that the first is about the simulation result, is accuracy is in line with the expectation, and the second is the pores in the epoxy do not have so many influence on the mechanical performance, and the third, the damage may initiate before the 1.5% loading point. And for the future work, I will do the idealist modeling and to introduce the debonding using introduce a cohesive element in the model to simulate the debonding behavior, and hopefully it can match the experiment results. And thank you for the supporting from all the people. And yeah, if you have any questions, happy to ask. Happy to answer. Thank you.